operational K-theory. Thank you.
Okay, so thanks very much to both of the principal organizers for the invitation. So what I'm talking about is not, has nothing to do with the structure of algebraic groups, but rather using algebraic groups in their actions on varieties. And in fact, the group is the simplest group that there is. So the only group that will appear is a split torus. So this is a very different kind of point of view, but I'm just trying to make the connection to some things that have been said before. Before I forget, because I do sometimes, so anything I say today that I claim to be new is joint with Sam Payne, and then we have some kind of work in progress that I'll talk about, but probably not till tomorrow, that's joint with Richard Gonzalez. Well, with the three of us. Okay, so the setup is I'm going to take a variety over an algebraically closed field. And so let me just say just a few general words about K-theory and where this comes from. So a basic question is if you've got basic question and problem is if you've got a vector bundle a vector bundle, you may want to know some things about this vector bundle. So like you may want to know something about what its global sections are, or sort of a better behaved variant of that is what is its holomorphic Euler characteristic, which is just defined to be the alternating sum of the cohomology sheaves. So can you compute that? And this leads, and I guess this is somehow what led Grothendieck to define K-theory. So the Euler characteristic is additive on exact sequences. So that is to say that if you have an exact sequence of vector bundles, then you have a simple formula like this. And that means that it becomes a function on the quotient of isomorphism classes. A vector bundle is modulo a relation that just says you consider the middle term the sum of the two outer terms whenever you have such a short exact sequence. So it's a function on what's called the K-theory of X, which is defined to be just isomorphism classes of vector bundles modulo the relation that E equals E prime plus E double prime whenever you have such an exact sequence. Okay, so the study of such groups is kind of a major topic in mathematics, and I don't have. One of the story I'm going to tell you is about kind of an approach to studying a very simple piece of some of these groups. So that's what I'll tell you. Yeah. Let me say something. So let me say something else. There's another thing you can do. So this is contravariant in X. You can pull back a vector bundle if you have a map between varieties. You can pull back a vector bundle, and so it acts like a cohomology theory. So a cohomology theory wants a homology theory to pair with, And this one has a nice homology theory to pair with. So there's a corresponding homology theory. So and that is, I'll write with a lower 0, k lower 0 of x. You basically are going to do the same thing, but instead of, I guess I should have said here, I'll write it. I'm going to perform the same construction of a group. But instead of taking as input vector bundles, I'm going to take as input a coherent sheaf. Coherent sheaf on X. Modulo the same kind of relation for any exact sequence of coherent sheaves. So this is some bigger class of objects you can associate to X. And this is covariant for proper maps. So as Professor Brion said in the first lecture, so proper is this algebrogeometric version of compact, and well, this is the algebrogeometric version of saying that the inverse image of a compact is compact, whatever that means. So you can push forward via proper maps. And so how do these relate? Well, you can take, so given a class in K theory in K upper 0, so you can act on K lower 0 by tensor product. So you can take any coherent sheaf and tensor it by a vector bundle that defines an action. And in particular, so this is, so the way I'll write this is just, so if alpha is the class of a coherent sheaf, then the class that you get by tensoring by a vector bundle, I'll just write it with a dot. But in particular, you have a homomorphism from K upper 0x to K lower 0x, just taking a class and tensoring it by the structure sheaf of X, which is also a trivial vector bundle. Or, so that equivalently, just consider as a coherent sheaf. As a coherent sheaf. So vector bundles are special kinds of coherent sheaves. And this is, this defines this map. And a basic fact is that this is an isomorphism. If X is smooth. So this is sort of the Poincare duality in this kind of cohomology theory. Okay, so now I'm going to introduce the only group that's going to play a role. So there are equivariant versions so and in fact you could take any group you like here, but I'm only going to be talking about a torus. So here T is a torus, and well, we know what tori are, I guess, now, but I'm just thinking of it as some product of copies of the multiplicative group, and it's acting on X. And you can ask that, so these groups are defined in exactly the same way, but you construct them from equivariant vector bundles. So that is to say, you're given your action of the torus on X, and it lifts in a linear way to an action on E such that the structure of this map is preserved. Equivariant vector bundles, and there's a way of defining this similarly for equivariant coherent sheaves. So let me give just a kind of trivial example. Oh, right, but first I want to say something a little bit more. Yeah, I guess this is okay. So what's a vector bundle, an equivariant vector bundle on a point? An equivariant vector bundle on a point is just a way of making T act on a vector space. So this is just, and there's a ring structure here, I guess. I didn't say what the ring structure is, but so the tensor product, this also defines ring structure on the K-theory group itself. So it really does act like a cohomology theory. It's got a ring structure. But the ring structure is just tensor product, and this is the representation ring. Well, we can say exactly what the representation ring is. So for a split torus, any representation splits into copies to one-dimensional representations. So you just need to keep track of the characters. And since I'll use this notation, I'm going to write this. I'll write it out. So here M is the group of all homomorphisms, algebraic group homomorphisms from T down to the multiplicative group. So this is the character group. Of T. And it's nice to write these kind of in exponential notation. So the group algebra of this is going to just get written this way. So there's a basis one for every character. Yeah, okay, so just to be really kind of explicit, so e.g., yeah, I wanted to use this one. So if I've got a two-dimensional torus that acts on a two-dimensional vector space by, as follows, just like T1 inverse X to T1 inverse T2 Y. So this representation corresponds to, in this group algebra, it's going to correspond to e to the minus u1. That's going to be the character that corresponds to T1, plus e to the minus u1 plus u2. So I'm just setting up notation really here. Okay, so I said that, that this is a contravariant. Oh, this doesn't go up anymore. So K-theory vector bundles is contravariant in X, and so if you have a you have restriction maps, so I'll just say this now. If you've got a map that is an equivariant map of varieties, then you get restriction maps from X down to Y. The case that's very interesting to look at is the case when Y is the fixed point set of the torus action on your variety. So that's definitely an equivariant map because the torus acts trivially here. So we get a map. And you can get a lot of mileage out of looking at what happens under this map, and that's part of what I'm going to try to explain. So just for another concrete example, continuing this one, so let's let our torus, our two-dimensional torus, act on P2 just really explicitly by taking T1, T2 times X, Y, Z, just to be X, T1Y, T2Z. Just kind of the standard action on P2. And I'm going to draw a picture and then just kind of explain what I'm doing. So the tangent bundle is equivariant for this construction. There's a natural lift of this action to the tangent bundle. And so what happens to the K-theory class of the tangent bundle under these restriction maps? Let me show you. Oh, but before I do this, sorry, this should go up here. So the fixed locus for this particular action is just 3 points. So the coordinate points, basically. So I'll call those P1, P2, P3. And so the tangent bundle is equivariant, and I want to kind of study it by restricting to these fixed points. So I've got K-theory of P2, and the class of the tangent bundle sits in here. And I can restrict to the fixed locus, but since this is just 3 copies, just 3 points, this is going to be 3 copies of the representation ring. So it's just the representation ring 3 times. And well, what happens here? You just take the vector bundle and then in each factor take it to the representation that is the fiber, the tangent space in this case at that point. So the kind of tangent space at that point as an equivariant, as a representation. So let me actually just do that just to kind of keep working this example. So I'm going to just put in the top right P1, the top left P2, and below P3, and I'm just going to write down what the character is. Well, here you can work out pretty easily from the action that, and it's no surprise, that the representation is just this kind of standard representation. Here it's, I hope I got it right, it's this one. Or you just kind of change coordinates. And here it's this one. Okay. So it's kind of a remarkable fact that in this case, and I'll say a little bit more about this next time. So in this case. So let me call this map I pullback because it's the pullback for the inclusion of the fixed point. In fact, this is injective. And this is a remarkable and remarkably useful fact because it says that you can study anything about vector bundles on P2 or equivariant vector bundles on P2 just by restricting to this finite amount of data. Okay. And this is more, so this case here is, for example, smooth, projective with finitely many fixed points. There are weaker hypotheses that also give this, but in fact, it's quite easy to prove that this is injective in this under those hypotheses. Okay, so let's see. Let me say something a little more generally about toric varieties. So for those who know a little bit about toric varieties, this will make sense. And for those who don't, a toric variety is P2. So that's basically what I'm talking about. So you need to take the dual, just the linear dual of the character group. So this is the group of one parameter subgroups of the torus. And I'll always write n sub r to be n tensor with r. And of course, if m is just z to the n, I guess I didn't say this before. So m is isomorphic to z to the n. And so then its dual is also isomorphic to z to the n. And so in particular, n r is isomorphic to Rn. Okay, so what you can do is you can take what's called a fan in N. And this is just a collection of convex cones that fit together. And I'll put in fitting together along faces. Basically, just like a simplicial complex does. So here we have an example of a fan in R2, and so there's three big cones. So here's a cone, it's just spanned by these two vectors. Here's another cone that's spanned by these two vectors, and they're convex cones, and they fit together along their rays. So given this data, there's an algebraic variety denoted x delta. It's a toric variety defined over K, and it comes with an action of the torus with a dense orbit. Okay. So associated to a toric variety, so given a fan, something like this is just some convex geometric object, you can associate a space. You can also associate a ring which I'll call px of delta. So these are piecewise exponential functions on the fan. And these are just continuous functions. So the support of the fan, this is just the union of all cones. So this is a collection of cones. In this case, the support of the fan is all of R2, right? Because all the cones fill out R2. So it's continuous functions that satisfy. Oh, oops. So I'll write this down, then I'll have to define the notation. For each cone, the restriction, I can just look at this function and restrict it to the cone. This lies in a certain quotient group algebra, which I'll say what it is. So also for each cone, you always have this quotient, which is just the quotient by kind of the linear dual. All the functions on the cone that vanish. So yeah, all the functions that vanish along the cone. And this induces such a so it's something that you just associate. So you're just associating some kind of exponential function to each cone, and they should glue together in a nice way. And let's just kind of take a look. It so happens that I've written down one of these guys here, because look, if you restrict this function to, I guess this is the u1 axis, this is the u2 axis. Restrict this function to the u1 axis, that means u2 is 0, right? So this becomes e to the u1 plus 1. And if u2 is 0, well then it's the same thing. So this is 1 plus e to the u1. And you can check that these things glue up nicely in all the other cones as well. Okay. And so I guess what I'm saying is there's a natural map. Let me write this as a theorem. Right here. So there's a theorem which I know to attribute to Brion and Verne in one context, and a little later in a somewhat more general context, or different context really, Betzozzi and Vistoli. So the natural restriction map, so for x smooth, the natural restriction map defines an isomorphism from the K-theory of x onto piecewise exponential functions on the fan. So let me kind of cast this in another way. We started with some combinatorial data. There's two ways to associate a ring to it. First, at least the way I'm telling the story, you build a space, a toric variety, and if you don't know what that is, I mean, think of it as just a way of getting a ring, and then you take the K-theory of that toric variety, and that gives you a ring. On the other hand, you could define just a completely combinatorial object, this piecewise exponential functions on the fan, and so then it becomes a kind of a reasonable question to ask what's the relation between the two, and in the smooth case, it turns out they're isomorphic. So for me, that's sort of where this, let me call this star. That's sort of where this project got started, with trying to understand to what extent you could extend this past the smooth case. Let me also mention, again in the smooth case, because so also in the smooth case, there's an older theorem. And I guess this is Buffet, De Concini, and Procesi. And in one context, and Brion in another context. The theorem is that, so you could take a more familiar cohomology theory, like just ordinary cohomology, again, assuming that this thing is smooth. Then ordinary equivariant cohomology is isomorphic to Chow cohomology, and they're both isomorphic to, so these are piecewise polynomial functions. And these guys won't make it another appearance, at least today. But you can think of it as the analog of this, except instead of saying that these are exponentials, they're just going to be polynomials. So one way to get them would be to take some version of leading order terms. Well, no. Yeah, it doesn't have to be complete. At least for this statement, it doesn't actually have to be complete. And so no, it also does not have to be complete. Yeah. Right. So maybe, yeah, let me just leave it like that. Okay, so, right, a motivating goal was to try to do this So this is basically how Sam and I got involved in this. We thought we'd just extend these theorems to the singular case, and that we'd be done in a couple of weeks. And it took a couple of years, but the payoff was nice because it turned out to have applications. Well, I guess I would say that our main applications are still within the world of toric varieties, but somehow the theory that developed out of it seems to be interesting outside of just the world of toric varieties. And between today and tomorrow, I'll try to convince you that that might be true. But let me say some things in general about how bad K-theory might be for singular varieties. So in general, it's a hard thing to get your hands around. And well, first of all, here's a question that is partly motivating us as well. Does X even have a vector bundle, a non-trivial vector bundle? So it's not at all obvious that if you take a singular variety, you might not even be able to embed it in any non-singular variety. And in that situation, it's certainly not obvious how to get non-trivial vector bundles on X. So unfortunately, our methods basically will not shed any direct logical light, although they might be motivating. What we do is so this is a technical kind of remark, we're going to use K-theory of perfect complexes. So this is instead. So so the K-theory that behaves nicely somehow doesn't actually say anything about vector bundles directly. But I'll say something about that. So, well, how else is it hard? So it's not homotopy invariant. So what that means is that if you so for a singular variety, there's a natural map from K-theory of X to K-theory of X cross A1 just by pulling back by along the projection, and this is not, in general, an isomorphism. And let's see what else. It might be big, kind of, let me say, unexpectedly big. So for very simple varieties like toric varieties, like projective space, at least people like me that are kind of combinatorial, kind of have a combinatorial frame of mind, we get used to thinking, well, these varieties have very simple and kind of tractable cohomology theories. But as Gubaladze showed, even for projective toric threefolds k0x could be uncountable. I mean, so from certain points of view, if you allow, I mean, if you take x to be, even a smooth, like an abelian variety, this will certainly be uncountable. Well, you say if k is, so it might contain a copy of the field. But for toric varieties, this is somehow unexpected. And yeah, basically, all of these things kind of come together to say that it's hard to compute. Okay. So I'm going to shift gears and say something about, so I've said some things about K-theory, and then I started talking about toric varieties, but the title of the talk was operational K-theory, so I want to tell you a little bit about what operators are. So operational cohomology. So this is going to be about a 5-minute digression, and then I'll come back to the main thread of the story. So in the 80s, so Fulton and McPherson were building intersection theory. And they wanted a cohomology theory to pair with the homology, so Chow homology. So these are cycles modulo rational equivalents. And basically, they found that this was hard to do. So what they did was they defined, I'm not going to give you the full list of axioms because it's not terribly enlightening, but they defined this Chow cohomology. So I'll just tell you what an element of this is. So an element of this is a tuple of operators, sorry. Of endomorphisms of homologies, one for each map of a variety y into X. Put this one up here. Satisfying some compatibilities. And all you need to think about to figure out what the compatibilities are is like the cat product between cohomology and, so ordinary singular topological cohomology and homology. So that's what the compatibilities are. So a priori, this sounds like a unreasonable thing to do, because you're defining an element to be, well, an operator for every map of a variety into your fixed variety. Yeah. And it seems like it might be kind of intractable. But it turns out not to be. So I guess I just did this. I lost the t, but you can imagine putting in a t. So rather than, so you can require everything to be equivariant as well. So I'll tell you a couple of theorems, and then so there's this theorem that's kind of the analog of this one. And this is our starting point. And this is basically why we thought things would be fairly easy. So there's a similar story. There's a restriction map in Chow cohomology for any toric variety, for any fan delta. There's a natural restriction operator, just like before. And so this is always an isomorphism for any. And so now I guess I don't even really need to write down the theorem that we proved, because it was, well, but I will. It's kind of the thing that you would guess given this. So given I guess the parallel is not, the wires got crossed, but the parallel of this statement turned out to work out by taking operational Chow cohomology. And so it seems to make sense to guess that the parallel of this should also work that way, and it does. So any delta, you have there's an operational K-theory that I'll tell you about for the rest of today, and it becomes isomorphic to piecewise exponential functions on the fan. So and this here is what operational K-theory is. So what do I mean by operational K-theory? Well, operational Chow cohomology takes as input Chow homology and then produces a cohomology thing that acts on it just by fiat. And op K is defined by kind of applying Fulton-McPherson's construction starting with K lower naught, the homology theory of coherent sheaves, instead of Chow. So in other words, an element of operational K-theory is a tuple of operators on all K-theories of K homologies for all maps Y mapping into, for all varieties Y mapping into X. It's the same kind of thing as before. So let's see. So what I'd like to do is so basically, this is kind of, for us, this is kind of a cute story. This is kind of nice that, well, we found some more or less geometric theory that associates, that kind of identifies what this combinatorially defined ring is in a geometric way. But we also found some applications outside of the world of just operators and combinatorics. And I think what I'll do is I'll tell you about those next time, but I want to tell you now something about how to think about this stuff, and how to see that it's actually tractable. Okay. Yeah, good. Okay, so there we go. Great. So that was the first theorem I wanted to write down. So it turns out to be, so if X is smooth, the natural map, and you can do this with or without the torus, but So there's a natural map, sorry, this is op K. There's a natural map that takes an operator in here to just operate on the structure sheaf, right? You know, X maps into itself by the identity map, so I guess I should call it ID in there. And this is an isomorphism. No. Let me see. For smooth Y mapping, I don't think so, but in a sense that I'll make precise within 10 minutes, you can reduce to the smooth case. And, let's say in characteristic 0, if you have resolution of singularities, you can do this. And if you tensor with Q, you can do it using alterations. But yeah, I'll show you. I'll write down the theorem.
These isomorphisms of production, how they constructed?
These ones? Right. So. Yeah, so this is, okay, so this guy. Sits inside of, how do I want to put it? Let me do the case, let me answer your question in the case that you have a complete variety with finitely many fixed points. So then, so this is kind of, by construction, this is contravariant. You can pull back an operator just by evaluating on Y instead of X. And so you have a pullback map to the fixed locus. And this here, because this is smooth, we already know what this is. This is going to be just copies of the representation ring. So, and one knows kind of because it has to factor through all curves, that it therefore this maps the image in here, so it does map into piecewise exponentials, and this is the map. So it's this map. That's right. That's the right thing to say. Yeah, all orbits. So it's a right. I guess the right thing to say is this sits inside all cones. Just compose. So there, another way of saying this that maybe would have helped, this is just an endomorphism of, so up there, should I stay in K theory or not? Well, since I'm staying in K theory, I'll stay in K theory. So CG is an endomorphism of KY. So, yeah. And so it's just composition of endomorphisms. Yeah. Okay. So this is true. So in the smooth case, everything is kind of understood. And I guess there's also this maybe I can put it here too. So there's a natural map from K-theory of vector bundles or perfect complexes to operators. Basically, this is the operator. So a vector bundle goes to the operator, just multiplied by that vector bundle. And in the smooth case, well, we knew that there was an isomorphism here, and this factors that isomorphism. So maybe I should have said, yeah. Okay, so here's another theorem about operational K-theory. Oh, wait, I think I'm doing this out of order. Yeah. Okay, so suppose you've got what's called an abstract blow-up square. I'll just call it a blow-up square. And all that means in this context is that F is proper, and it maps, you should think of E as being the exceptional divisor over something that you're blowing up. So it maps the complement isomorphically onto this complement. And I guess S and X is closed. So then there's an exact sequence. So this is basically the key to everything that we do with operational K-theory and why it's useful. So 0 maps to op K X maps to op K. So this embeds the K-theory of X into the K-theory of the blow-up, and the co-kernel is just the sum of the two other pieces. So this is sort of a descent statement for operational K-theory. So the two of these, you now see how, you can kind of see how when you have resolution of singularities, you can reduce by induction on dimension and by the smooth case most computations to the smooth case. And indeed, that's how this theorem is proved. It's also how
So there's an equinary version of the alterations
oh, yeah, I said that. So, okay, so I should be careful. So, I don't know, but it might be, if it's sufficiently functorial, then it's not, right? Okay.
Choose curve vibration.
Yeah.
I think in a follow-up paper you did do the line. Anyway, whatever.
Yeah, okay, so in characters, well, okay. In characteristic 0, there's certainly no problem. And I guess if you forget the torus, then there's also no problem. So I'll try not to write down any statements that step outside of those cases. Oh man, I just didn't want to, well, okay, so I just erased all the bad things, or maybe not bad, but difficult things about regular K-theory. So one of them was that it was hard to compute, and I guess this theorem says that at least for toric varieties, it's operational K-theory is not so hard to compute, and more generally, this gives you a tool for computing operational K-theory of other varieties. So op K is computable.
What's the map? I mean, I'll describe the implicit map from the middle term to the second factor
So it's restriction and so there's two. Yeah.
Oh, it's kind of coherent with power analysis. Or nuts. Right. Nuts.
Did I say something weird? Oh man, I did. I'm sorry. I wrote this down wrong. Yeah, thank you. So one of them was clear and the other one was wrong. Yeah, okay. Yeah. So now it makes sense. Or these are the two pullbacks, and then and these are the different. This is the difference. Good. So the other little theorem, I guess this is not so hard to prove, is that so the pullback map is always an isomorphism, so it's homotopy invariant. Any way you like. And let me say, so the last thing that I'll say is that, in fact, so opk is universal in some sense. So in the following sense. So here I do want to use, so at least I'm going to use some category where I have resolutions of singularities. So let me just okay, so characteristic 0. So the theorem is that, and I can do this with the torus or without, but let's say this is any, say ring valued or group valued functor, so group valued. So schemes are finite type and separated over a field, such that, so with a natural isomorphism, so restrict this functor to smooth schemes. So this, if this becomes isomorphic to K-theory, the vector bundle is restricted to smooth schemes. Then there's a unique extension of eta to a natural transformation, taking L to op kt. So this is saying, so op k is the is a Kahn extension of k from along the embedding of smooth schemes in all schemes. So let's see. So that's, I guess, as good a place to stop for now. So what I hope to have at least kind of argued is that this is, in some sense, a natural thing to consider, and it's a useful thing to consider, at least from the point of view of having nice properties and being computable. Next time, I'll try to argue that it also gives us at least some new theorems about ordinary K-theory of toric varieties. And I guess the place that I'll start is, or one of the places I'll start is the kind of one natural thing you should think about when I've talked about K-theory, and somewhere along the line I talked about Chow homology and cohomology, And there should be a Riemann-Roch transformation that relates the two, and indeed there is. So that's what I'll talk about next time.
Any questions?
Is it possible to say just something briefly maybe about what kind of makes this group of this theorem tick?
This one?
Yeah.
Well, so in Chow theory, Kimura proved something that looks almost identical to this. And the key ingredient is a dual sequence that, so Gillet proved for the non-equivariant case, and we just slightly souped it up for the equivariant case. So it's a dual sequence on K theory. So at the same setup, you've got so once you prove this, so this is some kind of homological descent for K theory, then this is kind of a formality.
But when you say that like this theory is computable, I mean computable as resolution of singularities, or of course for toric varieties it's
Yeah, maybe that's the right thing to say. So for toric varieties, resolution singularities is completely computable, and so therefore this is completely computable.
You still need to know the image of the last time. This setup of Gillet, does this sequence continue?
Yes, it does. So there's I mean,
You get the higher
and you can use that as well. So that's I don't want to get too far ahead, but that's part of what I'll talk about next time too. There's another theory that sits in between K theory of, okay, so there's another theory that sits in between these two. That,
So you get some higher population of K-field?
okay, so that's something that we haven't thought about really. And yeah. I mean, one question is like, so you could operate on, rather than just operating on K lower zero, you could operate on all higher K theory. But it's not at all clear that the kind of zeroth component of the resulting collection of operators is the same as the one that's just defined by operating on K lower zero. And yeah.
If you have a projective variety of finite